I just want to give a quick sort of overview of my perspective of what's going on with building decarbonization right now. And as you all know, buildings and infrastructure account for nearly 39% of all global CO2 emissions. So if we're embarked on decarbonizing buildings, we've picked a very important place to apply our intelligence. A relatively new activity is the ASHRAE Task Force for Building Decarbonization, of which I'm a member. And we are trying to reorient ASHRAE, which has been at the forefront of building energy efficiency, arguably for at least 40 years. I know I gave my first presentation at an ASHRAE conference in 1977, and it was essentially about building thermal modeling, but they've had the ASHRAE Standard 90. I can't remember, the first one of those was maybe 1975. So been in the building energy efficiency space for quite a long time, and we're trying to reorient them into the building decarbonization space, of which energy efficiency is an important part, but it's not the only part. I'm also working on a couple of I'm involved with a couple of working groups that are supporting New York City Local Law 97. And that is a building carbon emissions limitation law. The working groups are informing New York City Department of Buildings on the process of writing the regulations that implement this law. And here's the time frame that we are looking at. It's a very complex issue, lots of different stakeholders with lots of very different agendae. And so we're just trying to get something on the books with regard to the regulations in concert with this this schedule. So 4 basic steps to building this decarbonization: maximizing the energy efficiency of the energy consuming systems within the building, elimination of consumption of CO2 equivalent energy sources within the building by electrification or substitution of renewable delivered fuels, decarbonization of the electric grid, and minimization of refrigerant leaks or substitution of non-CO2e refrigerants. So when we're looking at maximizing building energy efficiency, we go through a process of adding different energy conservation measures, and this is a graphic from the ASHRAE Advanced Energy Design Guide for Zero Energy K-12 schools. And I was on the committee that wrote that document, but showing the different types of the application in appropriate order of the different energy conservation measures and the impact of those measures on the building EUI. So there are 4 issues. If we are going to talk about alternative fuels, non-CO2e delivered fuels, we need to evaluate them from 4 different perspectives. And so those 4 perspectives are sourcing overhead. What damage does the creation of this fuel do to the planet? Conversion efficiency. How efficient is the conversion of this fuel to the desired end uses, recognizing that people don't need energy. People need light. They need to make it to the 35th floor without having to walk all the way. They need their iPad to work. Those are the things that they need. And the question is, how efficient is a particular fuel toward meeting those desired end uses? And we need to look at the entire chain of conversion, and I'll address that in a moment. We need to look at energy transport, because almost certainly the source of the fuel is not the place where it will be used at the end. So how efficient, safe, and cost effective is it to transport the fuel from its place of manufacture to the end use location? And then finally, energy storage. How safe, easy, and space or mass efficient is the fuel to be stored for later end use conversion? Realizing that, only a very few delivered fuels will actually be delivered to the site on an as needed basis. Some of them will be delivered in bulk, and the question is, how bulky are they if we have to have them delivered and then store them for use over a period of time? So comparing the different alternative fuels, many of these, and with regard to the greenhouse gas emissions compared with fossil fuels, standard fossil fuels, we see that some are much better than others, but this is only addressing the carbon emissions component. The other components, some of these may have a very low carbon emissions characteristic, but they may be very hazardous to the environment for other reasons. So there's a multiplicity of issues with regard even to something like the sourcing overhead. So there, and even something like biomass, for example, there are challenges to the implementation of biomass for use for renewable energy. And as you may well know, many locations in Europe are in fact getting their a low carbon rating through the use of wood pellets that are sourced from the United States and are arguably being produced in a very non-sustainable manner. So if we look at something, for example, like agricultural waste and conversion of that to a renewable fuel, a non-CO2e delivered fuel, we look at the energy density of the raw source, and this waste product has a very low energy density, and that decreases the effective collection radius. So just do a little arithmetic around this. Lower heating value of the agricultural waste, how much electricity does it produce, what are the maximum losses for material handling, how much does it how much energy is consumed by the collection vehicle, and we wind up with a number that 80 miles is the maximum radius for waste collection for this biofuel to have a net positive energy characteristic. So when we when we talk about decarbonization of buildings and removal of CO2e fuels, we're basically talking about replacement of the fuel for three processes in the building, and those are space heating, service or domestic water heating, and cooking. And there are some good technologies increasing in efficiency as we go along to providing those end uses in using electricity as a fuel. So we have air source heat pumps. We have heat pump water heaters. And we have electrical induction cooktops, which I did a little investigation of, and turns out that in many cases the carbon emissions, total carbon emissions per, let's say, unit mass of cooked foods is less for this all-electric source than it is for gas. And the reason for that is with the induction cooktop, if you size the pan to the size of the piece of food that you're cooking, there's far less transmission of heat, loss of heat to the kitchen environment than there is with gas. Arguably, gas burner, puts a small percentage of the heat into the food and the rest goes into the room. But if you have an appropriately sized pan with an induction cooktop, most of the heat goes into the food. So, when we talk about electrifying space heating, one of the things that we really need to look at is the concept of harvesting internal heat gains within the building to deploy to the building perimeter to meet the heating loads at the perimeter. So I know in Santa Barbara you don't have this issue, but in New York City we do. And so this is looking at an energy modeling, a graph of energy modeling results for a short period of time, several days, for a building in New York City. And what we have in blue is the outdoor temperature, and what we have in aqua is the thermal balance of the building, showing that it is in a significant deficit for some time and in a significant surplus at other times, and it goes back and forth depending upon whether it's a work day or a weekday, and depending upon the weather. And so arguably the most energy efficient place to harvest heat is from inside the building itself, if that exists. And you can see here all of a sudden that the how relevant thermal storage becomes, because if we've got this surplus, it would be terrific if we could park it someplace and then use it to meet this the thermal deficit that is going to occur later on. We have some challenges with regard to the electrification, let's say, of either space heating or domestic hot water. And this is more or less to scale, showing the size of a 6 million BTU an hour boiler, gas-fired, and 6 million BTUs an hour of air source heat pump capacity. And while the relationship between the space requirement and the first cost is not completely linear, there is a significant relationship. So clearly this alternative is going to cost many times more first cost than is this alternative, and we need to overcome that issue. So when we talk about the key strategies for building electrification, they do vary by climate. So if we look at heating climate, strategies for electrification there are to configure the space heating system to use the lowest possible source temperature. Most of the older buildings in New York City that have hydronic heating, the systems, the baseboard convectors, the coils and the fan coils or what have you, they're sized for 200-degree hot water approximately. Why is that? Because that is the lowest first cost alternative. And before we had condensing gas boilers, there was really no energy efficiency advantage to be gained by producing hot water at 140 degrees or 120 degrees compared to 200 degrees. But arguably the first cost of implementing a system in terms of the size of the pipes, in terms of how much coil you have to have at the point of use to transfer the heat to the space, the first cost of heating with 200-degree hot water is much less than the cost of heating with 100 or 120 degree hot water. However, when you get into an electric sourced heating alternative, using some type of refrigeration cycle to make the hot water with heat sourced from either the outdoor air or inside the building, you'll be much more energy efficient if you can do that with a low temperature as compared with a high temperature. Use passive heat recovery for all effluents in the building, exhaust air, wastewater, etc. All of those sources of heat are going to be at a much higher temperature throughout much of the heating season than is the outdoor air. So if you can do that, and in fact, we just finished working on a project for a very large existing building with a lot of exhaust and a lot of ventilation air, but the exhaust outlet and the ventilation air inlet are not co-located, so very difficult to do any kind of passive heat recovery. So what we're doing is we are installing an air conditioning system that will air condition the exhaust air, drop it from whatever it's being exhausted at from the building, 72 or 74 degrees, down to 40 degrees Fahrenheit. And we can use the rejected heat from that to supplement the space heating requirement in the building. And the COP of doing that is much better than the COP of extracting that air from 20 or 25 degree Fahrenheit outdoor air. Obviously, and that's an example of harvesting all internal heat gains by active cooling and use the rejected heat for space heating. I used to think I was so smart when I configured my system to do free cooling all winter long, not realizing that I'm throwing away a valuable resource. That heat could be used to heat the building if we were to harvest it, and that's the strategy that we're pursuing on a number of buildings, both new buildings and retrofit in New York City, to try to let no BTU escape without being exploited to the maximum extent. Obviously, we want to minimize the envelope and infiltration heat losses because that will lower the balance point temperature of the building. That is the temperature at which the building reverts from being thermally positive to thermally negative. And so that reduces the number of hours in which we will have to go to the outdoor air as a thermal resource to heat the building. Humid climates, different strategies. Important strategy whenever you're doing dehumidification is to separate the dehumidification from the sensible cooling, because the dehumidification requires low temperature. You have to take some volume of air down to a temperature generally lower than about 53 or 54 degrees Fahrenheit to get a dew point temperature that will be consistent with maintaining comfort conditions in the space, which 75 degrees Fahrenheit, 50% relative humidity, which is a 55 degree dew point. So doing the arithmetic, and what's really interesting, much of the analysis for these kinds of things just is really accessible, at least in a sort of back of the envelope way, by very simple arithmetic. So we want to separate this dehumidification, because we need the low temperature cooling to do that, from the sensible cooling, which we can do with a much higher temperature. And so, for example, if we're making 42 degree water for the dehumidification, we will wind up with a chiller with an efficiency of between 0.55 and 0.6 kW per ton. Whereas if we're making 55 degree water to do the sensible cooling, we're looking at a chiller that's going to be operating at 0.40, 0.41 kW per ton. So that's a very significant decrease in the amount of energy required to do the same amount of cooling, all because we're cooling at the appropriate temperature. And also in humid climates, recovering the dryness from the exhaust air. So enthalpy wheels that recover dryness from the exhaust air to partially dehumidify the incoming ventilation air. Dry climate strategies control the solar heat gain to provide space heating when necessary and to avoid overheating when you don't need that heat. Provide all cooling at the highest possible temperature because you don't have to dehumidify. Consider solar thermal domestic hot water and use free cooling, air side economizer, or natural ventilation when no space heating is required. Those are very, general rules of thumb, but a guideline for strategies to pursue. So we look at the typical energy conversion path and once again apply a little arithmetic to it. We start with our fossil fuel, which we burn to generate heat flow, and then we take that steam through a turbine and make kinetic energy, which turns a generator, which makes electricity, and we transport that across the country, and we put that into our refrigerator, which might have a COP of somewhere around 2 or 2.5 or something like that. And what we get for making cooling, which is our end use that we're focusing on this case. So a BTU of fossil fuel results in 0.54 BTU of cooling inside your refrigerator. So we need to keep track of the entire energy conversion sequence from the source to the end use. So when we look at electrification and grid decarbonization, we can look at the multiple steps. The first step is where we are base case with our on-site natural gas, and then basically we go to our heat pump technology, so that the only fuel that's actually being delivered to the building for all of its end uses is electricity and heating, domestic hot water provided by heat pump, and then ultimately when we have the entirety of the grid decarbonized, then we wind up with our carbon-free solution. We've heard some discussion about the duck curve and this basically in this case what we're looking at here is for the CAISO over an average day, what are the number of megawatts that are produced from non-renewable sources, and we can see these are dropping, and this is what ultimately predicted, and we have an issue at some point where the contributions of customer renewables is in fact greater than the power need beyond the non-controllable base load generation, and the utility has to begin to curtail its renewable production in order to maintain the stability of the grid. And when we look at your basic net zero building, what we see is that it is got its photovoltaic production, it's got its building demand, and when we concatenate those two together, what we see is that we are wanting to export this green segment to the grid precisely during the time when the grid doesn't want it. Okay, and this is a significant problem. Obviously, different areas have different curves of this type, and here we're looking at curves for different types of days. In the Southwest Power Pool, I think that's called, New York ISO, CAISO, and ERCOT, which is Texas, I believe. And so different curves. And so what that means is that if we are to intelligently operate our building to minimize the total carbon emissions for supplying the energy needs and the electrical needs of the building, we'll need different strategies in different locations. And this is a problem even in Europe. This is something I pulled off the internet for Germany, showing two different kinds of days and showing a problem here where we've got zero wind and 16% hydro biomass and the issue there. And here we have basically we have 97% renewable, and very likely we're going to have some curtailment of that of the utility renewables because of customer renewable contribution. So energy storage is the key to aligning the grid and the building. Obviously, behavioral change is one characteristic, but as we saw, you know, looking at the thermal balance of the building, behavioral change isn't going to get you past that problem, and you need thermal storage. So here we have this is a flow diagram for an ice making system, and some images of some ice making systems that I was involved with in the past. But in the circumstance of decarbonization, they may be used differently because apropos to a comment I made earlier today, in the past, ice storage was implemented to reduce peak demand, which typically would occur, you know, in mid-afternoon of a hot, possibly sunny summer day. And so basically you would provide all the cooling needs for your building outside of that peak period with your regular chiller plant, but you would try to shave as much as possible of the peak demand during using the chiller. But in a decarbonization scenario, it works differently, because what happens is we're going to do all of our refrigeration during the middle of the day when the sun is out, and we have significant photovoltaic contribution either to the grid or to the building or both. And then once we get outside of this period when the sun is shining, we're going to do all that cooling with the ice we made up here. A completely different scenario. No longer managing congestion, but now trying to shift our electric consumption to periods of time when the sun is out and the PVs are producing. So we have both customer electrical storage, and we have utility storage. Here is a pumped hydro installation. Both of these are very important. The grid can raise its we can store electricity generated by renewables during the period of time that's available by pumping water into this upper reservoir, and then it will recover it by allowing it to come downhill through turbines to generate electricity when there's not so much renewable content on the grid. But that's really not that capable of dealing with some of the very local issues. So the point here is that both of these are very valuable to the decarbonization effort. Just wanted to talk a little bit about refrigerant leakage, something that's overlooked, but there are some studies out there that indicate that the CO2 emissions from refrigerant leakage or cooling systems is about 25 to 30% of the total cooling system's emissions over the life of the system, which is a big deal. And so addressing this whole life cycle refrigerant leakage issue. What happens when you originally make it, when it's originally transported, when the equipment is charged, what happens during servicing, during the life of the equipment, and then what happens to the refrigerant when the equipment goes out of service. Very big, very important issue for CO2 equivalent emissions. And just finally, some notes. Igor asked me to talk briefly about the impact on the COVID pandemic on building decarbonization. Just a few points. Carbon emissions from buildings and construction fell significantly in 2020, but significant reliance on coal may offset any gain because of the supply chain issues with regard to natural gas and some other fuels. Remote working lowers both building internal heat gain and ventilation requirements. So if you've got a building which is harvesting internal heat and nobody's there using their computer, there's less heat to harvest. But on the other hand, the ventilation requirements are less, and so the heat loss from ventilation would be less. Aerosol-free air to limit virus transmission can either be outdoor air or highly filtered air. And so the ASHRAE Task Force, Epidemiological Task Force, established some guidelines for air turnover and air delivery, and really stressed the importance of maintaining something like 6 air changes per hour through MER 14. And to do that would require extensive modifications to most existing HVAC systems. However, HVAC systems that separate temperature control from dehumidification can maintain high air turnover rates with minimum energy efficiency. Our conventional, in dehumidifying climates, our conventional VAV system keeps a constant supply temperature to control the dew point and varies its cooling capacity by varying the airflow. However, much of the time, that system will be operating at far below the 6 air changes per hour required to take the aerosols out of the air. So separating so that you do the dehumidification through the outdoor air ventilation stream, which is constant, and then doing the sensible temperature control with turnover through some local fan coil or something like that, where you can vary the supply air temperature to vary the capacity and not vary the airflow and thus the turnover across the filters. In New York City, the business downturn caused by the pandemic does not seem to have reduced investment in building carbon emissions mitigation for compliance with NYC Local Law 97 that imposes these fines for emissions from prescribed limits. I'm seeing a lot of projects, working on some of them, that are looking at electrification and significant decarbonization, and that doesn't seem to be have been impacted that much by the pandemic. And I'm over my time, so I apologize for that.
Thank you, Dan. As I said, we built some time into discussion time, so hope to find everybody. Any questions from the audience? I want to thank you for this very broad perspective. It tells us how many different aspects come into building an energy efficient solution when you're architecting a building that's as complex as say, NYT headquarters. But anyhow, any questions from the audience or the panelists or audience on this? So Tim has one.
Yeah, I have a quick question. Thank you, Dan. It was a really interesting presentation, very comprehensive. My question is just about electrification in general. Do you think that the drive and the interest, the fervor toward electrification is detracting or even supplanting the aspect of energy efficiency? So we can add all these electrical appliances, but how efficient are those electrical appliances that are going to electrify a building that then require just greater demands then? So what's thoughts around that?
So there's a lot of work going on studying that, and I mentioned that previously. for example, Manhattan and very, very substantial electrification of space heating and domestic water heating in Manhattan likely would not change it from, or if it did change it to winter peaking, it would be by a very small margin that it became winter peaking. But I think the answer is no. We are, out there in the field, we are still very interested in energy efficiency, and we are searching around, for the highest efficiency air source heat pumps. And when I come up with a new one that at 0 Fahrenheit and 100-degree water supply is a COP of 2.4 rather than 2.25, I mean, that just made my day, right? So no, we are definitely looking at that with the realization that in the long term, yes, energy efficiency will be important, but substituting an air source heat pump for a very efficient, 95% efficient condensing gas boiler is a move for the future.
Yeah.
All right.
Just can I ask one follow-on too? Is about the. So I mean, we've had so much focus on space heating and cooling, and we've done a really good job there, I think. But then you go into office buildings today, and especially the younger generation, they have so many electrical devices, then they plug into the outlets and their destination. So we have massive increase in plug load. Is that just going to offset all the work we've done on the space heating and cooling side of things, do you think?
If anything, we are seeing plug loads begin to go down. So that began 15 some odd years ago when we started to get flat screens instead of CRTs for a computer. And now everybody's doing a laptop rather than a desktop. And we're also seeing, this is within the confines of the building, right? We're seeing cloud computing happening, and that's taking the electric load out of the building and putting it someplace else, right? Yes. So to the extent that we are increasing our computational consumption, that may be ultimately increasing the grid-wide electrical load. But on the other hand, maybe not, because all the improvements, and this is far beyond my area of expertise, but virtualization and all those kinds of things, arguably, high temperature chips and locating the data centers in Montana or Maine or something like that. Basically, all you need is a moderately good-sized electrical pipe and a gigantic data pipe, and it really makes sense to locate the computer in a place where you can do free cooling the entire year with no. And when you take the when you take the electrical requirement for active cooling away from that, that will pay for a significant amount of additional computational consumption. So, yeah, I don't think, what we're seeing in buildings is that when we're doing these studies for harvesting internal heat gains going forward, we're making ridiculously low assumptions about the plug loads, because that seems to be the trend that's going on.